Hey guys, welcome again to this video. So in this video we are going to understand the beta function. The beta function is basically a function where we would be doing all those things which we did in the gamma function, and the beta function is basically an integral representation, and this integral representation can be done in terms of the gamma function, which you should see very soon. Because for, let me just write down, for AB greater than 0 we have, so we write the beta using beta, of course. Beta a comma b would be just equals to so for positive reals a and b we have the beta function, which is this, and the beta function can be expressed in form of the gamma function as gamma of a into gamma of b divided by gamma of a plus b. So well, this is something we can always find out, and in relation to this we can also find the beta distribution, but what we are trying to do here is we are trying to prove this. So let us try and get on with our proof. Let's see how we can prove it. So proof. So in order to prove this we first need to understand, and we need to understand how to prove it essentially. So because if you want to prove this thing exactly, it won't happen. So what we are trying to prove is the following. So we would rather be proving that gamma of a into gamma of b would be equals to gamma of a plus b multiplied by the integral 0 to 1 t to the power a minus 1 and 1 minus t whole to the power b minus 1 dt. So proving this is a bit easier than proving gamma of a plus gamma b by gamma of a plus b directly. So well, this would give you the same answer obviously. Now how do we again start? Well, if you remember from the last exercise where we had proved the Euler reflection formula into an integral form, what we did is as follows. We represented gamma and gamma b in terms of its integral representations, right? So gamma of a should be and gamma of b should be e to the power minus y to the power b minus 1 dy, right? So gamma of a and gamma of b. Now when you multiply this two, as we have seen in the previous sections, what we do is we use a double integral, because that is why we have used different variables to represent them. So e to the power minus x, e to the power minus y, x to the power a minus 1, y to the power b minus 1, and we can write dx dy. Well, this would be our representation, right? Now again, with this representation, what we would be trying to do is we would be trying to make some changes to it. So we'd be trying out a substitution. We still do not know what substitution would be the best, but well, we have idea of what to substitute to make it into a function that we know. So like you understand, in the previous example, what we did was we substituted u equals to x by y. So it may not be a bad idea to try the same, because it may well be the case that this u equals to x by y could do wonders again. So let us try that first. If that fails, we can try something else. Let's start with the substitution. U equals to x by y. So this basically means x equals to uy, right? And let's say keep y constant, and what we get is this. Keeping y constant, what we will get is dx equals to y into du, right? Because we have kept y constant, or let's say y fixed rather. So what will this give us? This will give us like this: gamma of a into gamma of b would be equals to, the outer limit was y equals to 0 to infinity, so it's a good time to start naming. And this now would be basically u equals to 0 to infinity. So u equals to 0 to infinity, and we have dx equals to, so let me just write down everything here. X would be uy, so e to the power minus uy, e to the power minus y, it would be uy to the power a minus 1, and this would be y to the power b minus 1. It should be du into y, and this should be dy, right? So this would be the entire integral. Now if we were to arrange it accordingly, we would get y equals to 0 to infinity, and this would be e equals to 0 to infinity, and it will become e to the power minus y into u plus 1, u to the power a minus 1, y to the power a plus b minus 2, minus 1 actually, because we have another y in here, and then we will have du and dy. So as you can see, this is the expression that we have. So we need a gamma a plus b, as you remember, because that's what we are trying to prove. So what we can do is we can evaluate the y integral first as follows: u equals to 0 to infinity, u to the power a minus 1, and inside keep the y integral, y equals to 0 to infinity, e to the power minus y into u plus 1, y to the power a plus b minus 1 dy, and then we have the du. Now this type of integral is very familiar to us. It's the generalized version of the e to the power minus ax x to the power n dx for 0 to infinity, which basically evaluated to gamma of n plus 1 by a to the power n plus 1, if you remember. So I'll just write it down. Note that for n greater than minus 1 and a greater than 0, 0 to positive infinity, e to the power minus ax x to the power n dx basically was gamma of n plus 1 by a to the power n plus 1, right? So therefore gamma of a into gamma of b would then be u equals to 0 to infinity u to the power a minus 1 multiplied by gamma of a plus b divided by 1 plus u whole to the power a plus b du, and this then would be equal to gamma of a plus b into 0 to infinity. Now since we have a single variable, we do not really need to change the variable of integration. U to the power a minus 1 into divided by 1 plus u whole to the power a plus b du, right? So this would be how we change it. Now of course, if you can change this integral, you can also change the other integral. Now it's only a matter of time, because after we represent this integral as basically the integral that we want to represent it as, that is this integral, right? Right here, this integral. So how do we transform it? That's what we're going to see. So see, this kind of substitutions require careful observation, but since I'm already telling you, so let t equals to u by 1 plus u. So let us substitute this one. What happens is, firstly, if we were to evaluate du from there, what we can do is we can evaluate t into 1 plus u equals to u. Let's solve this first. T plus tu equals to u, and u became t by 1 minus t, right? Now from here, du should be 1 minus t whole square, 1 minus t plus, because minus it would be 1 minus t into derivative of t minus t into derivative of 1 minus t, which is minus 1, minus and minus is plus, so it would just be 1 by 1 minus t whole squared, right? And this would mean that we have 0 to infinity u to the power a minus 1 by 1 plus u whole to the power a plus b du equals to, now the limits. So for the limits, you know that from this definition we can find them out. So let's find it out here. T lower should be u lower by 1 plus u lower, and u lower was 0, I think, so it would be 0, right? And t upper should be limit of u tends to infinity u by 1 plus u, but this just evaluates to 1 by 1 plus 1 by u, which is 1, so the upper limit should be 1. So this should be 0 to 1. Now what we are trying to do here is u is t to the power a minus 1 by 1 minus t whole to the power b minus 1, and you have 1 plus u whole to the power minus of a plus b, and this means 1 plus t by 1 minus t whole to the power minus a minus b, and du is just dt by 1 minus t whole squared. So let us just simplify it further and see if we can get any results which are similar to ours. 0 to 1, and what we get is t to the power a minus 1 by 1 minus t whole to the power b plus 1. So we just combine this square with this one, and this 1 plus t minus 1 by t just becomes 1 by 1 minus t whole to the power minus of a plus b dt. This becomes 0 to 1 t to the power a minus 1 into 1 minus t whole to the power minus b minus 1, and this becomes 1 minus t whole to the power a plus b, because 1 by 1 minus t is already 1 minus t whole to the power minus 1, and the powers minus 1 and minus a plus b multiply out to give a plus b, and this gives you 0 to 1 t to the power a minus 1, and multiplying this, because they have the same base, the exponents will be adding up. You have 1 minus t to the power b minus 1, right? Oh, it was a, sorry, yeah. So this would be how we evaluate this integral, and this means that putting this back into this part, where was it, one second. Yeah, this part. Putting it back into this part, we get that gamma of a into gamma of b is basically equals to gamma of a plus b into 0 to 1 t to the power a minus 1 into 1 minus t whole to the power b minus 1 dt. Therefore 0 to 1 t to the power a minus 1 into 1 minus t whole to the power b minus 1 dt is equals to gamma of a into gamma of b by gamma of a plus b, which is the proof for the beta function. So I hope this was very entertaining and very resourceful for you. So we will continue the properties of the gamma function and beta function in the next video, along with a lot of interesting examples and a tougher ones, of course. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.